Imagine standing in a vast cosmic web, watching light travel across billions of light years. Now picture that same light confined to a single line, unable to spread, unable to curve, forced to move in only one direction forever. This is the journey we're about to take together, from the complexity of our three-dimensional universe to the stark simplicity of a world with just one dimension. Speed and space dance together in ways we rarely consider. When we measure how fast something moves, we are really measuring how it travels through dimensions: length, width, and depth. These three dimensions give meaning to every measurement we make, every journey we take, and every beam of light that reaches our eyes from distant stars. But what would happen if those dimensions simply did not exist? What if the universe contained only a single direction, a lone pathway stretching infinitely in both directions? In contemplating such a radically simplified reality, we uncover profound truths about how space, time, and light work together to create the very fabric of existence. Our universe is rich with complexity. Galaxies spiral in majestic arms, planets orbit in elliptical paths, and light radiates outward in all directions from every star. This complexity is not accidental. It emerges from the fundamental nature of three-dimensional space itself. Strip away these dimensions, and we strip away nearly everything we recognize as reality. Tonight, we will explore what remains when we reduce our universe to its most basic form. We will discover how speed itself depends on the dimensions it moves through, how light requires multiple dimensions to exist as we know it, and why the speed of light might have an entirely different meaning in a universe with only one dimension. This is not just a mathematical exercise. By imagining the impossible, we learn to appreciate the miraculous. By contemplating the simple, we understand the profound. Our journey through one-dimensional space will illuminate why our own universe works the way it does, and why the dimensions we take for granted are actually the foundation of everything we experience. As we begin this exploration, let the complexity of our three-dimensional world fade into the background. Picture a single line stretching endlessly in both directions. This line is our new universe, and everything we think we know about speed, space, and light is about to change. The cosmic web dissolves into simplicity, and our adventure into the nature of dimensions begins. Welcome to a universe where forward and backward are the only directions that exist, where light as we know it cannot shine, and where the very concept of speed takes on an entirely new meaning. Welcome to one-dimensional space. Speed seems like such a simple concept. We measure it every day when we drive, when we run, when we watch a bird fly overhead. But speed is far more profound than we usually consider. It is not just how fast something moves, it is how something moves through the very fabric of space itself. Speed is intimately connected to the dimensional structure of reality, and understanding this connection reveals deep truths about the nature of existence. At its most basic level, speed is distance divided by time. Take a car traveling 100 kilometers in 1 hour. We say it moves at 100 kilometers per hour. Simple enough. But hidden within this simple calculation lies a deep truth about the nature of reality. That distance, those 100 kilometers, can only exist because space has dimensions through which the car can travel. Without dimensions, without length and width and depth, there would be no framework for measuring distance at all. In our three-dimensional universe, distance is never just a single number. It is a combination of movements through length, width, and depth. When you walk from your kitchen to your bedroom, you might think you are moving in a straight line, but you are actually navigating through three-dimensional space. Your path has components in multiple directions, even if you are not consciously aware of them. The hallway might force you to turn slightly. the floor might slope imperceptibly, and you might adjust your height to duck under a light fixture. This is where vectors come into play. A vector is not just a speed, it is a speed with direction. If you tell someone you are moving at 50 kilometers per hour, you have given them incomplete information. Are you moving north, south, up, down? The direction matters just as much as the speed itself. In three-dimensional space, every movement can be broken down into components along three perpendicular axes. Each component tells us something different about the motion. Imagine you are walking diagonally across a large field. From above, your path might look like a straight line from one corner to the opposite corner. But mathematically, your movement has two components. You are moving forward and you are moving sideways simultaneously. Each component has its own speed, and when combined, they create your overall velocity vector. This is the essence of displacement in three-dimensional space. The beauty lies in how these separate components work together to create the actual motion you experience. Think of a baseball flying through the air after being hit by a bat. The ball moves forward toward the outfield, but it also moves upward against gravity, and it might move slightly to the left or right, depending on how it was hit. Its velocity is a combination of all three movements happening simultaneously. This is displacement, the change in position through three-dimensional space. Each component of motion tells a different part of the story. The forward component might be 80 kilometers per hour. The upward component might start at 30 kilometers per hour, but decrease as gravity pulls the ball down. The sideways component might be just 5 kilometers per hour. Barely noticeable, but still present. Together, these three components create the graceful arc we see as the ball flies through the air. The trajectory exists because three-dimensional space allows for this rich interplay of motions. Now consider something moving much faster. A jet aircraft cruising at 900 kilometers per hour is not just moving forward. It is moving forward, slightly upward to maintain altitude, and perhaps slightly sideways to adjust for wind currents. Even at such high speeds, the aircraft's movement is fundamentally three-dimensional. The pilot must constantly make small adjustments in all three dimensions to maintain the desired flight path. The wind itself demonstrates three-dimensional complexity. Air moves not just horizontally, but also vertically, and in swirling patterns that exist in three-dimensional space. Turbulence creates eddies and vortices that extend in all directions. The aircraft must navigate through this three-dimensional fluid, responding to forces that come from every direction. Without three-dimensional space, there could be no atmosphere, no weather, and no flight. The speed of light itself is measured using these three-dimensional frameworks. Scientists have developed ingenious methods to calculate exactly how fast light travels. Time-of-flight experiments send light across known distances and measure how long it takes to arrive. In 1849, Hippolyte Fizeau used a rotating toothed wheel to measure the speed of light between two mountaintops. The wheel would spin, allowing light to pass through the gaps between teeth, travel to a distant mirror, and return. By adjusting the wheel's rotation speed, Fizeau could determine how long the light took to make the round trip. This experiment required careful three-dimensional alignment. The light beam had to travel in a straight line through three-dimensional space, reflecting off a precisely positioned mirror and returning to the exact same location. The rotating wheel had to be positioned so that the light could pass through the gaps at exactly the right moment. Every aspect of the experiment depended on the three-dimensional geometry of the setup. Interference experiments use the wave properties of light to create patterns that reveal its speed with incredible precision. When two beams of light meet, they can interfere with each other, creating bright and dark bands. By measuring these patterns, scientists can determine the wavelength of light. Combined with measurements of frequency, this gives us the speed of light with extraordinary accuracy. These interference patterns exist because light waves can spread through three-dimensional space and overlap with each other. The bright and dark bands form complex two-dimensional patterns that reveal the three-dimensional nature of wave propagation. Without multiple dimensions, there would be no way for waves to interfere and create these revealing patterns. More modern experiments use lasers and atomic clocks to measure the speed of light to within a few parts per billion. These experiments rely on sending light through carefully controlled three-dimensional paths, measuring the time it takes with atomic precision, and calculating the speed from the known distance. The laser beams must be aligned through three-dimensional space with incredible accuracy, and the measuring apparatus must account for every possible three-dimensional effect that might influence the results. Atomic clocks themselves depend on three-dimensional atomic structures. The atoms that keep time do so because their electrons occupy specific three-dimensional orbitals around the nucleus. The energy transitions that mark the passage of time occur when electrons move between these three-dimensional quantum states. Even our most precise measurements of time depend on the three-dimensional nature of matter. Every measurement of the speed of light relies on our three-dimensional understanding of space. We measure the distance light travels through length, width, and depth. We track its path as it moves through our three-dimensional laboratory equipment. We observe its behavior as it interacts with three-dimensional objects like mirrors, lenses, and detectors. The mirrors used in these experiments have three-dimensional surfaces that reflect light according to the three-dimensional geometry of the setup. Lenses focus light by bending it through three-dimensional space according to the laws of optics. Detectors capture light using three-dimensional arrays of sensors that convert electromagnetic energy into electrical signals. The famous Michelson-Morley experiment, performed in 1887, sent light in perpendicular directions and measured whether it traveled at different speeds. This experiment, conducted in three-dimensional space, helped establish that the speed of light is constant in all directions. It also provided crucial evidence that eventually led to Einstein's theory of relativity. The perpendicular arms of the Michelson-Morley interferometer existed in three-dimensional space, allowing the experimenters to compare light traveling in different directions simultaneously. The interference patterns they observed were two-dimensional projections of three-dimensional wave phenomena. The null result they obtained was profound, precisely because it demonstrated that three-dimensional space does not contain a preferred reference frame. But what makes these measurements meaningful is not just the numbers we obtain. It is the dimensional framework that gives those numbers context. Distance only makes sense when there is space for something to move through. Speed only makes sense when there are dimensions that define what movement means. The very concept of measurement depends on having a rich enough spatial framework to support the measurement process. Consider how we actually experience speed in our daily lives. When you walk down a street, you are not just moving forward. You are navigating around other people, stepping over cracks in the sidewalk, adjusting your path to avoid obstacles. Your movement through space is constantly three-dimensional, even when you think you are just going from point A to point B. Your legs move in complex, three-dimensional patterns as you walk. Each step involves lifting your foot up off the ground, swinging it forward through the air, and placing it down again ahead of you. Your arms swing back and forth to maintain balance. Your torso rotates slightly with each step. Your head moves up and down and side to side as you look around. Walking is a three-dimensional dance that engages your entire body. Even the simple act of turning a doorknob involves three-dimensional movement. Your hand rotates around an axis, creating angular velocity. Your fingers apply force in multiple directions. The entire motion is a complex dance through three-dimensional space, even though it seems effortless and natural. The doorknob itself is a three-dimensional object that rotates around a three-dimensional axis Embedded in a three-dimensional doorframe, your nervous system coordinates these movements using three-dimensional information processing. Your inner ear detects rotation and acceleration in three-dimensional space. Your eyes track objects moving through three-dimensional scenes. Your brain integrates all this three-dimensional sensory information to create a coherent understanding of your position and motion in space. The same is true for light. When light leaves a star, it does not just move in one direction. It radiates outward in all directions simultaneously, creating an expanding sphere of electromagnetic energy. This spherical expansion is only possible because space has three dimensions. The light can spread out, it can curve around massive objects, it can interfere with itself to create complex patterns. The star itself is a three-dimensional object held together by the three-dimensional gravitational field it creates. Nuclear fusion occurs in the three-dimensional core, where temperatures and pressures are high enough to overcome the electromagnetic repulsion between atomic nuclei. The energy released by fusion travels outward through the three-dimensional structure of the star, eventually reaching the surface and radiating into space. A single photon from a distant star has traveled through the three-dimensional fabric of space for millions or billions of years. It has navigated around planets, been bent by gravitational fields, and possibly scattered by interstellar dust. Its journey to your eye is a testament to the three-dimensional nature of space itself. The fact that we can see stars at all depends on the ability of light to propagate through three-dimensional space across cosmic distances. The gravitational lensing that bends starlight around massive objects demonstrates the three-dimensional curvature of space-time. Light follows geodesics through the curved three-dimensional space around stars, galaxies, and clusters of galaxies. These gravitational effects allow astronomers to study distant objects and even to detect otherwise invisible dark matter through its gravitational influence on light. Speed becomes rich and meaningful precisely because it occurs within this three-dimensional framework. Velocity vectors can point in any direction. Objects can rotate, creating angular velocity. Waves can propagate in complex patterns, creating interference and diffraction. All of these phenomena emerge from the dimensional nature of space itself. Consider the complexity of a spinning top. It has linear velocity if it is sliding across a surface, angular velocity as it spins around its axis, and precessional velocity as its axis wobbles. Multiple types of speed occurring simultaneously, all made possible by the three-dimensional structure of space. The top's motion combines translation, rotation, and precession in a beautiful display of three-dimensional dynamics. The physics of the spinning top reveals deep connections between space, time, and motion. Angular momentum is conserved because of the rotational symmetry of three-dimensional space. The precession occurs because gravity acts on the top's three-dimensional mass distribution. The stability of the spinning motion depends on the three-dimensional distribution of mass within the top. Even our units of measurement reflect this dimensional reality. When we say kilometers per hour, we are invoking a unit of distance that exists in three-dimensional space. A kilometer is not just a number, it is a measure of displacement through the spatial dimensions we inhabit. Time, while separate from space in our everyday experience, provides the framework against which we measure how quickly objects move through those spatial dimensions. The meter, the fundamental unit of length, was originally defined as 1/10,000,000th of the distance from the equator to the North Pole along the surface of the Earth. This definition required understanding the three-dimensional shape of our planet and the ability to measure distances across its curved surface. The modern definition based on the speed of light still depends on three-dimensional geometry and the propagation of electromagnetic waves through space. the mathematics of speed in three-dimensional space can become quite complex. Calculus helps us understand how velocity changes over time, creating acceleration. Vector analysis helps us break down complex motions into simpler components. Differential geometry helps us understand how objects move through curved spacetime. All of these mathematical tools exist because speed is fundamentally about movement through dimensional space. Calculus in 3 dimensions allows us to analyze how vector fields change from point to point in space. Gradient, divergence, and curl are 3-dimensional operations that have no meaning in lower dimensional spaces. These tools are essential for understanding electromagnetic fields, fluid flow, gravitational fields, and countless other phenomena that exist in our 3-dimensional world. When we study the motion of planets around the Sun, we use 3-dimensional vector equations to describe their elliptical orbits. When we analyze the flow of air over an airplane wing, we use 3-dimensional fluid dynamics equations. When we calculate the trajectory of a spacecraft traveling to Mars, we must account for 3-dimensional gravitational effects from multiple celestial bodies. Planetary orbits demonstrate the rich dynamics that emerge from 3-dimensional gravitational fields. The elliptical paths that planets follow exist in 3-dimensional space, with each orbit lying in a slightly different plane. The gravitational interactions between planets cause their orbits to precess slowly over time, creating complex 3-dimensional patterns that unfold over millions of years. Spacecraft trajectories must be planned using 3-dimensional calculations that account for the changing positions of planets, the influence of the solar wind, and the need to arrive at precise locations in 3-dimensional space. Mission planners use 3-dimensional computer simulations to optimize fuel consumption and timing for interplanetary voyages. But what if that dimensional framework did not exist? What if space itself had only one dimension? What would speed mean in such a radically simplified universe? What would happen to all the richness and complexity that emerges from 3-dimensional movement? This question challenges us to think about what is truly fundamental about motion and what emerges from the specific dimensional structure of our universe. In a one-dimensional universe, there would be no vectors as we understand them, no angular motion, no complex trajectories. Every concept of speed and motion would be reduced to its absolute simplest form. This is where our journey becomes truly interesting. To understand what speed means in one-dimensional space, we must first strip away everything we take for granted about movement, direction, and displacement. We must imagine a universe so simple that forward and backward are the only directions that exist. We must contemplate what remains when the dimensional richness of our reality is reduced to its absolute minimum. The transition from 3-dimensional to 1-dimensional space is not just a mathematical exercise, it is a profound shift in how we think about the nature of reality itself. As we prepare to make this journey, let us remember that everything we have discussed about speed, vectors, and measurement exists because our universe has the dimensional structure it does. Strip away those dimensions, and we strip away nearly everything we recognize as physical reality. Yet this stripping away reveals something profound about the relationship between space and the phenomena that occur within it. By imagining what would be lost in a simpler universe, we gain deeper appreciation for the richness and complexity of our own. The dimensional structure of space is not incidental to physics. It is fundamental to everything we observe and experience. In the next part of our exploration, we will enter this simplified universe and discover what remains when space itself becomes nothing more than a single line stretching infinitely in both directions. We will see how the concept of speed persists even in the most austere possible reality. And we will understand more deeply why the 3-dimensional nature of our own universe is so special and so essential to everything we know and love about existence. Close your eyes and imagine the most fundamental change possible to reality itself. Strip away the width of everything around you. Remove the height from every object you know. What remains is a universe of pure length, a reality where only one dimension exists. This is not merely a mathematical abstraction, it is a journey into the very foundations of what space means. We are about to enter a realm so alien to our experience that every familiar concept of motion, position, and existence must be reconsidered from the ground up. In our familiar three-dimensional world, you can move forward and backward, left and right, up and down. You can turn around, look over your shoulder, reach above your head. You can walk in circles, climb stairs, swim through water, fly through air. The richness of movement in our universe is so vast that we rarely pause to consider how extraordinary it is. But in one-dimensional space, all of these movements become impossible. There is only one direction, stretching infinitely in both directions, like an endless line drawn across the void. Picture this transformation happening gradually. First, imagine that you can no longer move left or right. You are constrained to move only forward and backward along a single path. Then imagine that the very concept of left and right disappears entirely. There is no sideways, no lateral direction, no way to even conceive of movement except along the single line that defines all of space. Finally, imagine that up and down vanish as well. There is no height, no depth, no way to lift your head or look down at your feet. All of existence is reduced to a single line extending infinitely in both directions. One-dimensional space is a mathematical construct that challenges everything we understand about movement and position. Imagine a perfectly straight line, thinner than the thinnest wire, thinner than any physical object that could ever exist, extending forever in both directions. This line represents the entirety of space in our simplified universe. Everything that exists, everything that moves, everything that could ever be, must exist somewhere along this single line. The line itself has no thickness, no width, no substance. It is pure mathematical abstraction, a set of points arranged in perfect order from negative infinity to positive infinity. Yet within this seemingly empty abstraction, we must try to understand what reality might mean. What could exist on such a line? What kinds of entities could inhabit this one-dimensional universe? Position in this universe becomes remarkably simple. In our three-dimensional world, you need three numbers to specify exactly where something is located. You need an x-coordinate to tell you how far east or west you are, AI coordinate to tell you how far north or south you are, and a z coordinate to tell you how far up or down you are. These three numbers, working together, can pinpoint any location in our universe with arbitrary precision. But in one-dimensional space, position is just a single number. You might be at position 0, or position 1000, or position -57. That single number tells you everything there is to know about where you are. There is no ambiguity, no additional coordinates needed, no complex three-dimensional geometry to consider. Your position is simply a point on the infinite line. Consider what this means for objects in such a universe. A particle at position 10 can only move to position 9 or position 11 or to any position in between. It cannot step sideways because there is no sideways. It cannot jump up because there is no up. It cannot rotate because rotation requires at least two dimensions to define the plane of rotation. The particle's entire existence is confined to moving back and forth along this single line. The concept of rotation, which is so fundamental to our three-dimensional experience, simply does not exist in one-dimensional space. There are no axes around which to rotate, no planes in which rotation can occur. An object in one-dimensional space has only one degree of freedom, its position along the line. It cannot spin, it cannot tumble, it cannot orient itself in different directions. Orientation itself becomes a meaningless concept when there is only one dimension. This constraint creates a universe of profound simplicity and equally profound limitations. Two objects cannot pass by each other because there is no way to go around. If particle A is at position 5 and particle B is at position 7, and they are both moving toward position 6, they must collide. There is no other possibility. They cannot dodge, they cannot sidestep, they cannot take a different route. Every encounter between objects moving toward each other is destined to be a collision. Think about how this changes the very nature of interaction. In our three-dimensional world, objects can avoid each other, orbit around each other, or interact in complex ways that depend on their three-dimensional relationship. But in one-dimensional space, interactions are brutally simple. Objects either collide head-on, or they don't interact at all. There are no glancing blows, no near misses, no complex gravitational dances. Imagine the social implications if humans existed in such a universe. If you were walking down a one-dimensional street and someone was walking toward you, one of you would have to turn around and go back. There would be no way to politely step aside and let the other person pass. Every encounter would be a roadblock, every meeting a traffic jam. The entire concept of social organization would need to be completely reimagined. Traffic flow in a one-dimensional universe would be a nightmare of logistics. Cars could only move in single file, with no way to pass slower vehicles. Every traffic jam would extend infinitely in both directions, with no alternate routes available. The concept of a highway system with multiple lanes and complex interchanges would be completely impossible. But humans, as we know them, could not exist in one-dimensional space. Our bodies require 3 dimensions to function. Our hearts pump blood through 3-dimensional networks of veins and arteries that branch and merge in complex patterns throughout our bodies. Our brains process information through 3-dimensional neural networks, where billions of neurons connect to each other in intricate webs of synapses. Our lungs expand and contract in 3-dimensional space, creating the pressure differentials that drive respiration. Strip away 2 dimensions, and the very concept of biology becomes meaningless. Consider the complexity of even a single cell in our 3-dimensional universe. The cell membrane encloses a 3-dimensional volume, creating the fundamental distinction between inside and outside that defines life. Within this volume, organelles are arranged in 3-dimensional patterns that optimize their function. The cytoskeleton provides 3-dimensional structural support. DNA is stored in the 3-dimensional structure of the nucleus. Proteins fold into specific 3-dimensional shapes that determine their biological activity. None of this complexity could exist in one-dimensional space. There could be no enclosed volumes, no internal structures, no complex molecular machines. The chemistry that makes life possible depends entirely on the 3-dimensional arrangements of atoms and molecules. Without these dimensions, there could be no chemistry as we know it, and therefore no life. Even simple objects would be transformed beyond recognition. A one-dimensional table would be just a line segment. But what would it mean for this line segment to be a table? What function could it serve? In our universe, a table provides a horizontal surface that can support objects placed on top of it. But in one-dimensional space, there is no concept of on top, no way to place one object on another. The very purpose of a table disappears along with the dimensions that make it possible. A one-dimensional house would be a series of line segments connected end to end. But again, what would this mean? In our world, a house provides shelter by enclosing 3-dimensional space and protecting it from the external environment. In one-dimensional space, there is no internal space to protect and no meaningful concept of shelter. The house becomes a mathematical abstraction with no practical purpose. A one-dimensional car would be a point moving along the line with no wheels, no steering, no ability to change direction except by reversing. But cars exist to transport us through space efficiently. In one-dimensional space, where every journey is simply a matter of moving along the single available line, the concept of transportation becomes trivial. There are no roads to navigate, no destinations to reach that require complex pathfinding. Yet despite these limitations, time remains as a separate dimension. We have one-dimensional space plus one-dimensional time, creating what physicists call 1 + 1 dimensional spacetime. Time still flows forward, still provides the framework against which we measure change and motion. Events still happen in sequence, causes still lead to effects, and the arrow of time still points toward the future. This preservation of time is crucial because it allows for the possibility of change and motion even in the constrained environment of one-dimensional space. Without time, even this simplified universe would be completely static. But with time, objects can move along the line, accelerate and decelerate, and undergo changes that unfold over temporal sequences. This preservation of time creates interesting possibilities. Even though objects cannot move in multiple spatial directions simultaneously, they can still accelerate and decelerate along their single allowed path. A particle can speed up as it moves from position 0 to position 100, then slow down as it approaches position 200. The concept of velocity, as distance traveled divided by time elapsed, remains meaningful and important. The mathematics of motion in one-dimensional space becomes much simpler than in our three-dimensional world. Velocity is just a single number that can be positive or negative, indicating direction along the line. Acceleration is simply the rate of change of velocity. There are no vector components to track, no complex three-dimensional trajectories to analyze. Yet this simplicity allows us to focus on the fundamental nature of motion itself. In one-dimensional space, motion is pure displacement along the line. There are no rotational components, no complex curved paths, no centripetal accelerations. Motion is reduced to its most essential form, change of position over time. The physics of one-dimensional space becomes vastly simplified compared to our three-dimensional reality. There are no vectors in the traditional sense because there is only one direction. Vector addition becomes simple arithmetic addition of positive and negative numbers. There is no cross product because the cross product requires at least two different directions to be meaningful. There is no curl, no divergence, no complex vector field operations. There are no rotational forces because rotation cannot exist in one dimension. There is no angular momentum because angular momentum requires rotation around an axis, and axes cannot be defined in one-dimensional space. There are no gyroscopic effects, no conservation of angular momentum, no complex rotational dynamics. The rich complexity of three-dimensional physics collapses into a much simpler set of rules. Forces in one-dimensional space can only push or pull along the line. There can be no torques, no twisting forces, no forces that act perpendicular to motion. Every force simply accelerates objects forward or backward along their single allowed path. The vector nature of force is reduced to a simple scalar quantity, with a sign indicating direction. Gravity, if it existed in one-dimensional space, would behave very differently. In our universe, gravity pulls objects toward each other through three-dimensional space, creating the complex orbital mechanics we observe in planetary systems. The inverse square law of gravitation depends on the three-dimensional geometry of space, where gravitational field lines spread out over spherical surfaces, whose area increases as the square of the distance. But in one-dimensional space, gravity could only pull objects along the line. There would be no inverse square law, because there are no spherical surfaces for field lines to spread over. Instead, gravitational force might simply decrease linearly with distance, or follow some other rule determined by the one-dimensional geometry of space. Two massive objects in one-dimensional space would simply attract each other until they collided, with no possibility of stable orbits. There could be no planets circling stars, no moons orbiting planets, no complex gravitational interactions between multiple bodies. Every gravitational encounter would result in direct collision, with no escape trajectories possible. The absence of orbital mechanics eliminates one of the most beautiful and important phenomena in our universe. The dance of planets around stars, the formation of solar systems, the stability of planetary orbits over billions of years, all depend on the three-dimensional nature of gravitational fields. In one-dimensional space, none of this complexity could exist. The mathematics of one-dimensional space reflects this simplicity. Calculus becomes much easier when you only have one variable to worry about, instead of partial derivatives with respect to multiple spatial coordinates. You have only ordinary derivatives with respect to the single spatial coordinate. Differential equations become ordinary rather than partial, eliminating much of the mathematical complexity that characterizes three-dimensional physics. Integration becomes a straightforward process of finding areas under curves, rather than volumes under surfaces, or more complex geometric constructions. The fundamental theorem of calculus applies directly, without the complications of multiple integration or vector field integration that arise in higher dimensions. But this mathematical simplicity comes at a tremendous cost. The richness of three-dimensional geometry disappears entirely. There are no circles, no spheres, no complex curves winding through space. There are no surfaces, no volumes, no intricate three-dimensional structures. Everything collapses to points and line segments. Topology, the study of geometric properties that are preserved under continuous deformations, becomes trivial in one dimension. There are no holes to thread, no knots to tie, no complex topological structures to analyze. The topological richness that characterizes three-dimensional space is completely absent. Consider what happens to the concept of distance in one-dimensional space. In our universe, the distance between 2 points is calculated using the Pythagorean theorem. If you want to know the distance between your house and your workplace, you might measure the straight line distance through three-dimensional space. This calculation involves taking the square root of the sum of squares of the differences in x, y, and z coordinates. But in one-dimensional space, distance is simply the absolute value of the difference between two positions. If you are at position 10 and your destination is at position 30, the distance is exactly 20 units. No complex calculations required, no square roots, no vector mathematics. Distance becomes a trivial concept that any elementary school student could calculate. This simplification extends to the concept of speed as well. In three-dimensional space, speed is the magnitude of the velocity vector, which can point in any direction. Calculating speed requires taking the square root of the sum of squares of the velocity components in each direction. But in one-dimensional space, speed is just the absolute value of velocity. If something is moving at 5 units per second toward higher position numbers, its speed is 5 units per second. If it is moving at 5 units per second toward lower position numbers, its speed is still 5 units per second. The concept of acceleration also becomes simpler. In three-dimensional space, acceleration is a vector that can point in any direction, causing objects to change both their speed and their direction of motion. Centripetal acceleration causes objects to change direction while maintaining constant speed. Angular acceleration causes rotating objects to speed up or slow down their rotation. The interplay between different components of acceleration creates the complex motions we observe in our universe. But in one-dimensional space, acceleration can only make objects speed up or slow down along their single allowed path. There is no centripetal acceleration because there are no circular or curved paths. There is no angular acceleration because there is no rotation. There is no complex interplay between different components of motion. Acceleration is reduced to its simplest possible form, the rate of change of velocity along the line. Yet even in this simplified universe, the fundamental relationship between space and time remains. Motion still requires time, and time still provides the framework for measuring motion. The speed of an object is still distance divided by time, even though that distance can only be measured along a single line. The basic concepts of kinematics, dynamics, and mechanics still apply, though in greatly simplified form. This preservation of the space-time relationship raises profound questions about the nature of reality. If one-dimensional space can still support the basic concept of motion, what does this tell us about the fundamental structure of the universe? Are the three dimensions of space we experience truly necessary? Or are they simply the particular configuration that our universe happens to have? The question touches on deep issues in physics and philosophy. Is dimensionality a fundamental property of reality, or is it an emergent feature that arises from more basic principles? Could there be universes with different numbers of dimensions, each supporting different types of phenomena? What determines the dimensional structure of space, and why does our universe have exactly the dimensions it does? The answer lies in understanding what we lose when we strip away dimensions. We lose the ability for complex structures to exist. We lose the possibility of stable orbits, of biological organisms, of the rich interactions that make our universe interesting. We lose the ability for waves to propagate in complex patterns, for information to be stored in three-dimensional structures, for the emergence of complexity from simple rules. We lose the possibility of chemistry as we know it, because chemical bonds depend on the three-dimensional arrangements of atoms and electrons. We lose the possibility of materials science, because the properties of materials emerge from their three-dimensional crystal structures. We lose the possibility of engineering, because machines depend on three-dimensional mechanical principles. But we do not lose everything. We still have the basic framework of space and time. We still have the possibility of motion, of change, of events occurring in sequence. We still have a universe where things can happen, even if the range of possible happenings is severely limited. We still have the fundamental concepts of position, velocity, acceleration, and force, though in their most elementary forms. This realization prepares us for the next stage of our journey. We have established that one-dimensional space is possible, at least in principle. We have explored how objects might move and interact in such a universe. We have seen how the familiar concepts of physics are transformed and simplified when reduced to their one-dimensional forms. Now we must ask a more challenging question. Could light, or something like light, exist in one-dimensional space? Could there be a speed limit, a fundamental constant that governs how fast information can travel along our single line? What would electromagnetic waves look like if they could only propagate in one dimension? The answer to this question will reveal deep truths about the nature of light, the structure of space, and the fundamental laws that govern reality itself. As we prepare to explore these questions, let us remember that we are not just engaging in mathematical speculation. We are investigating the very foundations of existence, the basic principles that make our universe possible. In exploring what is possible in simplified dimensions, we gain deeper appreciation for the richness and complexity of our own three-dimensional reality. We begin to understand why our universe has the structure it does, and why that structure is so perfectly suited to supporting the complex phenomena we observe and experience. In one-dimensional space, we are about to discover even light itself must be reimagined. The electromagnetic waves that carry energy and information throughout our three-dimensional universe would need to be completely reconceptualized for a reality with only one spatial dimension. This reconceptualization will reveal fundamental truths about the relationship between light, space, and the ultimate limits of physical reality. Light, as we know it, is one of the most beautiful and complex phenomena in our three-dimensional universe. It dances through space as electromagnetic waves, creating the colors we see, carrying the energy that powers life on Earth, and traveling at the ultimate speed limit of reality itself. But could light exist in our imagined one-dimensional universe? The answer to this question reveals fundamental truths about the nature of electromagnetic radiation and the structure of space itself. To understand whether light can exist in one-dimensional space, we must first understand what light actually is in our three-dimensional world. Light is an electromagnetic wave, a self-propagating disturbance in the electromagnetic field that permeates all of space. This wave consists of two components that oscillate perpendicular to each other and perpendicular to the direction of travel. Imagine a beam of light traveling from left to right. The electric field component might oscillate up and down, while the magnetic field component oscillates forward and backward. Both fields are perpendicular to the left to right motion of the wave itself. This three-way perpendicular relationship is fundamental to how electromagnetic waves work. It requires three dimensions of space to accommodate the electric field, the magnetic field, and the direction of propagation. The electric field and magnetic field are not just mathematical abstractions. They are real, measurable quantities that exist in physical space. When you use a compass, the needle aligns with the magnetic field. When you rub a balloon on your hair and stick it to the wall, you are manipulating electric fields. These fields extend through three-dimensional space, and electromagnetic waves are disturbances that travel through this three-dimensional field structure. Consider what happens when light reflects off a mirror. The incoming light wave approaches the mirror surface at a specific angle. The electric field oscillates in a plane perpendicular to the direction of travel. When the wave hits the mirror, both the electric and magnetic field components interact with the electrons in the mirror's surface. The reflected wave emerges at an equal but opposite angle, with its field components rotated according to the three-dimensional geometry of the reflection. This reflection process requires the full three-dimensional structure of electromagnetic fields. The mirror surface exists in two dimensions. The incident and reflected waves travel in different three-dimensional directions, and the field components oscillate in planes that are defined by the three-dimensional geometry of the situation. Polarization provides another example of how light depends on three-dimensional space. When light passes through a polarizing filter, such as those used in sunglasses, the filter allows only the electric field component oscillating in one particular direction to pass through. This creates polarized light, where the electric field oscillates in a single plane. But even this single plane of oscillation requires two spatial dimensions to define it, plus a third dimension for the direction of propagation. In our one-dimensional universe, we face an immediate problem. There is only one spatial dimension available. We cannot have an electric field perpendicular to a magnetic field when there is only one direction in which fields can point. We cannot have both fields perpendicular to the direction of propagation when there is only one direction available for propagation. Classical electromagnetic theory, as described by Maxwell's equations, simply cannot work in one-dimensional space. Maxwell's equations describe how electric and magnetic fields create each other as they propagate through space. A changing electric field creates a magnetic field, and a changing magnetic field creates an electric field. This mutual creation allows electromagnetic waves to sustain themselves as they travel through empty space. But Maxwell's equations are written for three-dimensional space. they use vector calculus, which requires multiple dimensions to define vectors, curl, and divergence. In one-dimensional space, these mathematical tools lose their meaning. There is no curl of a vector field when there is only one dimension. There is no meaningful cross product between perpendicular vectors when perpendicular directions do not exist. Consider the famous relationship between the speed of light and the fundamental constants of electricity and magnetism. The speed of light in vacuum is equal to 1 divided by the square root of the product of the electric permittivity and magnetic permeability of free space. This relationship emerges from the three-dimensional structure of electromagnetic fields. In one-dimensional space, this relationship would need to be completely reconsidered. However, the absence of classical light does not necessarily mean the absence of all forms of information propagation. Even in one-dimensional space, we might imagine other types of signals or disturbances that could travel from one location to another. These would not be electromagnetic waves as we know them, but they might serve similar functions in terms of carrying information and energy. One possibility is a purely mechanical wave traveling along our one-dimensional line. Imagine a disturbance that propagates by compressing and expanding the fabric of one-dimensional space itself. This would be similar to a sound wave in air, where regions of higher and lower pressure travel through the medium. In our one-dimensional universe, such a wave might create regions of higher and lower density along the line. Another possibility is a quantum mechanical phenomenon that does not require classical electromagnetic fields. In quantum mechanics, information can be transmitted through quantum entanglement and other non-classical effects. Perhaps in one-dimensional space, quantum information could propagate at some fundamental speed limit, even without classical light waves. If such a signal existed in one-dimensional space, it might still have a constant propagation speed analogous to our speed of light. This speed could represent a fundamental limit on how fast information can travel along the one-dimensional line. Just as our three-dimensional speed of light sets the ultimate speed limit for information transmission, a one-dimensional universe might have its own ultimate speed limit. This hypothetical one-dimensional speed limit might be determined by the fundamental structure of one-dimensional space itself. Just as our three-dimensional speed of light emerges from the properties of electric and magnetic fields in three-dimensional space, a one-dimensional speed limit might emerge from whatever fundamental fields or structures exist in one-dimensional space. The measurement of such a speed would be much simpler than measuring the speed of light in our universe. There would be no need to worry about the direction of propagation, since there is only one direction available. There would be no need to consider wave polarization, interference patterns, or the complex three-dimensional geometry that affects light measurements in our world. To measure the one-dimensional speed limit, you might simply send a signal from position 0 to position 1000 and measure how long it takes to arrive. The speed would be distance divided by time, just as in our universe, but the simplicity of one-dimensional geometry would make the measurement much more straightforward. But what would such a signal actually be? Without electromagnetic fields, without the rich structure of three-dimensional space, what kind of disturbance could propagate along our one-dimensional line? This question touches on deep issues in physics about the relationship between space, fields, and information. One possibility is that the signal would be a disturbance in the metric of one-dimensional space itself. In Einstein's theory of general relativity, gravity is understood as curvature in the fabric of space-time. Perhaps in one-dimensional space, signals could propagate as tiny distortions in the geometry of the line itself, traveling at some fundamental speed determined by the properties of one-dimensional space-time. Another possibility involves quantum field theory, adapted to one-dimensional space. Even in one dimension, there might be quantum fields that permeate space and allow for the creation and propagation of particles and disturbances. These quantum effects might not resemble classical light, but they could still carry information and energy from one location to another. The mathematics of wave propagation in one-dimensional space is much simpler than in 3 dimensions. In 1 dimension, wave equations become ordinary differential equations rather than partial differential equations. Solutions are easier to find and analyze, but this mathematical simplicity comes at the cost of physical richness. The complex phenomena that make 3-dimensional light so interesting, such as interference, diffraction, and polarization, cannot exist in 1-dimensional space. Consider what happens when 2 one-dimensional signals meet. In 3-dimensional space, light waves can interfere with each other in complex ways, creating patterns of bright and dark regions. But in 1-dimensional space, 2 signals meeting at the same point must either add together or cancel out completely. There is no room for the complex interference patterns that create the beautiful phenomena we observe with 3-dimensional light. The absence of classical electromagnetic waves in 1-dimensional space also means the absence of many phenomena we associate with light. There would be no electromagnetic spectrum, no radio waves, no visible light, no X-rays, no gamma rays. There would be no radiation pressure, no photoelectric effect as we know it, no laser beams, no optical fibers. Yet the possibility remains that some form of information propagation could exist, governed by its own speed limit and its own physical laws. This hypothetical 1-dimensional signal might not be light as we know it, but it could serve the essential function of carrying information from one place to another at a finite, constant speed. The question of whether this speed limit would be constant, like our speed of light, depends on the fundamental structure of 1-dimensional space. In our universe, the constancy of light speed is tied to the principles of special relativity and the homogeneous, isotropic nature of 3-dimensional space. In 1-dimensional space, similar principles might apply, leading to a constant speed limit for information propagation. This constancy would have profound implications for the physics of 1-dimensional space. It would mean that the laws of physics would be the same at all locations along the line and at all times. It would provide a fundamental reference frame for measuring other speeds and for understanding the relationship between space and time in the 1-dimensional universe. As we contemplate these possibilities, we begin to see how the nature of light and information propagation is intimately connected to the dimensional structure of space itself. Light as we know it requires 3 dimensions to exist, but the concept of a fundamental speed limit might survive even in the stripped-down reality of 1-dimensional space. This realization leads us to our next question. If a speed limit exists in 1-dimensional space, would it play the same role as the speed of light in our universe? Would it be a fundamental constant that shapes the very fabric of reality, or would it be merely a technical detail in an impoverished physics? The answer will reveal whether the speed of light is truly universal, or merely a consequence of our particular 3-dimensional circumstances. The speed of light, universally denoted by the letter c, represents far more than just how fast photons travel through empty space. It is woven into the very fabric of reality, appearing in equations that govern energy, matter, time, and space itself. Einstein's famous equation E equals mc squared reveals that mass and energy are equivalent, connected by the speed of light squared. But in our imagined 1-dimensional universe, would this fundamental constant retain its cosmic significance? Or would it become merely a curiosity in an impoverished physics? To answer this question, we must first understand why c is so important in our 3-dimensional universe. The speed of light is not just the speed at which light travels, it is the speed at which causality itself propagates through space. It represents the ultimate speed limit for any information, any influence, any cause and effect relationship. Nothing can travel faster than c because doing so would violate the basic structure of space-time itself. This speed limit emerges from the principles of special relativity, which Einstein formulated in 1905. Special relativity tells us that space and time are not separate entities, but form a unified four-dimensional space-time. The speed of light is the conversion factor between space and time, determining how measurements of distance and duration change for observers moving at different velocities. In our three-dimensional world, the constancy of c has been tested with extraordinary precision. Scientists have measured the speed of light using rotating mirrors, atomic clocks, laser interferometry, and countless other techniques. Every measurement confirms that light travels at exactly 299,792,458 meters per second in vacuum, regardless of the motion of the source or observer. This constancy leads to the strange phenomena of special relativity. Time dilation causes moving clocks to run slowly. Length contraction causes moving objects to shrink along their direction of motion. Mass increases with velocity, approaching infinity as speed approaches c. These effects are not just theoretical curiosities, they are observed daily in particle accelerators, GPS satellites, and cosmic ray experiments. The mathematics of special relativity can, in principle, be adapted to one-dimensional space. The Lorentz transformations, which describe how space and time coordinates change between different reference frames, can be written for one spatial dimension plus time. This creates a two-dimensional space-time, where one dimension represents position along our one-dimensional line, and the other represents time. In this simplified space-time, a fundamental speed limit could still exist. Let us call this speed limit c1d, representing the maximum speed at which any signal or influence can propagate along our one-dimensional line. Just as c sets the ultimate speed limit in our three-dimensional universe, c1d would set the ultimate speed limit in the one-dimensional universe. The constancy of c1d would have profound implications for physics in one-dimensional space. It would mean that the laws of physics are the same for all observers moving at constant velocity along the line. An observer at rest and an observer moving at half of c1d would both measure the same value for the speed of the fastest possible signal, even though they are moving relative to each other. This constancy would give rise to relativistic effects in one-dimensional space. A clock moving at high speed along the line would run slowly compared to a stationary clock. This time, dilation effect would be described by the same mathematical formula as in our universe, but with c replaced by c1d. As an object's speed approaches c1d, its clock would run slower and slower, approaching zero rate as it reaches the speed limit. Length contraction would also occur in one-dimensional space, but its meaning would be different. In our universe, objects contract along their direction of motion, but remain unchanged in the perpendicular directions. In one-dimensional space, there are no perpendicular directions. Instead, length contraction would mean that the distance between any 2 points on a moving object, as measured along the line, would decrease when the object is in motion. The energy-momentum relationship of special relativity could also be adapted to one-dimensional space. In our universe, the total energy of an object is related to its momentum and rest mass. By Einstein's equation, E squared equals mc squared times c squared plus pc squared, where p is the momentum. In one-dimensional space, this might become E squared equals mc1d squared times c1d squared plus pc1d squared. This relationship would mean that as objects approach the speed limit c1d, their energy approaches infinity, just as in our universe. This infinite energy requirement would make c1d an unattainable speed limit for any object with mass, preserving the fundamental barrier between slower than light and faster than light motion. But would these relativistic effects matter in a one-dimensional universe? In our three-dimensional world, special relativity has practical consequences for technology, cosmology, and our understanding of the physical world. GPS satellites must account for relativistic time dilation to maintain accurate positioning. Particle accelerators use relativistic mechanics to accelerate particles to enormous energies. Astronomers observe relativistic effects in the light from distant galaxies. In one-dimensional space, the practical applications would be far more limited. There would be no GPS satellites because there would be no three-dimensional space for them to orbit in. There would be no particle accelerators creating complex collision patterns because particles could only collide head-on. There would be no galaxies because gravity could not create stable three-dimensional structures. Yet C1D might still play a fundamental role in whatever physics could exist in one-dimensional space. It would determine the relationship between energy and momentum for any particles that could exist. It would set the speed limit for any information propagation. It would define the structure of one-dimensional space-time itself. The question of whether particles could exist in one-dimensional space is itself complex. In our universe, particles are excitations in quantum fields that permeate three-dimensional space. These fields have rich mathematical structures that depend on the three-dimensional geometry of space. In one-dimensional space, quantum field theory would need to be completely reconsidered. However, some simple quantum systems might be possible in one-dimensional space. Quantum mechanics was first developed to understand the behavior of particles confined to specific energy levels, such as electrons in atoms. These energy level systems can be modeled as one-dimensional problems, where the electron's position along a single coordinate determines its energy. If quantum particles could exist in one-dimensional space, they would obey relativistic quantum mechanics adapted to 1 + 1-dimensional spacetime. The speed limit c1d would appear in the equations describing these particles, just as CE appears in our three-dimensional relativistic quantum mechanics. The electromagnetic spectrum, as we know it, could not exist in one-dimensional space because electromagnetic waves require 3 dimensions. But there might be other types of waves or excitations that could propagate along the one-dimensional line. These might create a simplified version of a spectrum, where different frequencies of one-dimensional waves carry different amounts of energy. If such a spectrum existed, C1d would appear in the relationship between energy and frequency, similar to how C appears in our electromagnetic spectrum. The energy of a one-dimensional wave quantum might be proportional to its frequency times some fundamental constant related to C1d. Angular momentum, which plays a crucial role in atomic physics and quantum mechanics, could not exist in one-dimensional space because rotation requires at least 2 dimensions. This absence would eliminate many of the quantum phenomena we observe in our universe, such as electron spin, orbital angular momentum, and the complex structure of atoms. Without angular momentum, there would be no Doppler effect as we know it. In our universe, the Doppler effect occurs when a source of waves moves toward or away from an observer, causing the observed frequency to increase or decrease. This effect depends on the three-dimensional geometry of wave propagation. In one-dimensional space, there would be no way for a source to move toward or away from an observer in any direction other than directly along the line. The absence of rotation also eliminates phenomena like polarization, which depends on the orientation of electromagnetic field oscillations in three-dimensional space. In one-dimensional space, there would be no transverse directions for fields to oscillate in, so polarization as we understand it could not exist. Gravitational effects in one-dimensional space would be severely limited compared to our universe. Einstein's general relativity describes gravity as curvature in 4-dimensional spacetime, with 3 spatial dimensions and 1 time dimension. In one-dimensional space plus time, spacetime curvature would be much more constrained. The speed c1d might still appear in a one-dimensional version of Einstein's field equations, playing a role similar to c in our gravitational theory. These equations would describe how matter and energy curve one-dimensional spacetime, and how this curvature affects the motion of objects along the line. But without three-dimensional space, there could be no stable orbits, no gravitational waves as we know them, and no complex gravitational phenomena like black holes or neutron stars. Gravity would be reduced to simple attractive forces between objects along the line, with no possibility for the rich dynamics we observe in our universe. Despite these limitations, C1d could still serve as a fundamental constant that shapes the basic structure of one-dimensional reality. It would determine the relationship between space and time, set the ultimate speed limit for causality, and appear in whatever fundamental equations govern one-dimensional physics. The measurement of C1d would be much simpler than measuring C in our universe. There would be no need to account for three-dimensional wave propagation, no complex interference patterns to analyze, and no directional effects to consider. A simple time of flight measurement along a known distance would suffice to determine the value of this fundamental constant. This simplicity might make C1d easier to understand conceptually than our three-dimensional C, even if its physical significance would be much more limited. The one-dimensional speed limit would represent pure, undiluted causality, the basic principle that causes must precede effects and that information cannot travel instantaneously across space. As we contemplate the role of C1d in one-dimensional space, we begin to see that fundamental constants are not just numbers, but reflections of the dimensional structure of reality itself. The speed of light c is important in our universe not just because light travels at that speed, but because c represents the fundamental relationship between space and time in a three-dimensional world. Similarly, C1d would be important in one-dimensional space, not because of the complex electromagnetic phenomena it governs in our world, but because it would represent the fundamental relationship between one-dimensional space and time. It would be a stripped-down, essential version of the speed limit concept, revealing the core principle that underlies all relativistic physics. This realization leads us to consider how the very concept of physical constants depends on the richness of the space in which they operate. As we continue our journey through one-dimensional physics, we will discover that reducing the dimensions of space changes not just the complexity of phenomena, but the fundamental meaning of the constants that govern them. Our journey through one-dimensional space has revealed profound truths about the nature of speed, light, and the very fabric of reality. By stripping away the familiar dimensions of width and height, we have uncovered the essential core of what makes our three-dimensional universe so rich, so complex, and so capable of supporting the intricate dance of matter, energy, and life itself. The contrast between our reality and the simplified one-dimensional world illuminates why speed in higher dimensions is inherently more meaningful, more powerful, and more beautiful than we might have imagined. In our three-dimensional universe, speed is never just a single number. It is a vector quantity that carries within it information about direction, magnitude, and the complex interplay between an object and the dimensional framework through which it moves. When a bird flies through the sky, its velocity vector captures not just how fast it is moving, but also its trajectory through three-dimensional space, its relationship to gravity, and its interaction with air currents that flow in three-dimensional patterns. This richness emerges directly from the dimensional structure of our space. In 3 dimensions, velocity can point in infinitely many directions. An object can move forward while simultaneously moving upward and sideways. It can accelerate in one direction while decelerating in another. It can rotate while translating, creating complex combinations of linear and angular motion that would be impossible in a lower dimensional universe. The mathematical beauty of 3-dimensional motion reflects this richness. Vector calculus, with its elegant operations of dot products, cross products, and curvilinear coordinates, captures the full complexity of how objects move through space. The cross product alone, which cannot exist in fewer than 3 dimensions, enables us to describe rotation, magnetic forces, and angular momentum. These mathematical tools are not mere abstractions. They describe real physical phenomena that emerge from the 3-dimensional nature of space itself. Consider the simple act of a planet orbiting a star. This motion requires at least 2 spatial dimensions to create a stable elliptical orbit, but it achieves its full beauty in 3-dimensional space, where the orbital plane can be tilted, where gravitational perturbations from other planets can cause precession, and where tidal forces can create complex, 3-dimensional deformations. The orbital mechanics that govern our solar system would be impossible in 1-dimensional space and impoverished in 2-dimensional space. The speed of light in our universe gains its cosmic significance precisely because it operates within this rich, 3-dimensional framework. Light does not simply travel from point A to point B. It radiates outward in all directions simultaneously, creating expanding spheres of electromagnetic energy that carry information across the cosmos. This spherical expansion is only possible because space has 3 dimensions for the light to spread through. When we look at distant stars, we are seeing light that has traveled through billions of years of 3-dimensional space. This light has navigated around gravitational fields, been bent by massive objects, scattered by interstellar dust, and Doppler shifted by the expansion of the universe itself. All of these effects depend on the 3-dimensional structure of space and the ability of light to propagate as electromagnetic waves through that space. The electromagnetic spectrum, from radio waves to gamma rays, exists because electromagnetic waves can oscillate at different frequencies while maintaining their 3-dimensional character. Each frequency corresponds to a different energy, creating the rich tapestry of electromagnetic radiation that powers stars, enables photosynthesis, and allows us to see the world around us. This spectrum could not exist in 1-dimensional space because electromagnetic waves themselves cannot exist without multiple dimensions. Interference and diffraction phenomena reveal another layer of richness that emerges from 3-dimensional light propagation. When light waves meet, they can interfere constructively or destructively, creating complex patterns that depend on the 3-dimensional geometry of the situation. These interference effects enable technologies like holography, interferometry, and many forms of precision measurement that would be impossible with 1-dimensional signals. The polarization of light provides yet another example of 3-dimensional richness. Light waves can be polarized in different orientations, with their electric fields oscillating in different planes perpendicular to their direction of propagation. This phenomenon enables technologies like liquid crystal displays, polarized sunglasses, and many forms of optical communication. Polarization cannot exist in 1-dimensional space because there are no transverse directions for the fields to oscillate in. Even the simple concept of brightness gains richness from 3-dimensional propagation. In our universe, the brightness of a light source decreases with the square of the distance because the light spreads over an ever-increasing spherical area. This inverse square law governs everything from the apparent brightness of stars to the exposure settings on cameras. In 1-dimensional space, there would be no spreading, no inverse square law, and no rich relationship between distance and apparent intensity. The measurement of light speed itself demonstrates the importance of dimensional richness. The historical experiments that determined the speed of light, from Romer's observations of Jupiter's moons to modern laser interferometry, all depend on the 3-dimensional propagation of light. These experiments use the geometry of 3-dimensional space to create known distances, to split and recombine light beams, and to measure the time delays that reveal light's finite speed. The constants that appear in electromagnetic theory, such as the electric permittivity and magnetic permeability of free space, are defined in terms of three-dimensional field configurations. These constants determine the speed of light through the relationship. C equals 1 over the square root of permittivity times permeability. This relationship emerges from Maxwell's equations, which describe the three-dimensional structure of electromagnetic fields. In contemplating one-dimensional space, we have discovered that these fundamental constants would lose much of their meaning. Without three-dimensional electromagnetic fields, without the rich interplay between electric and magnetic components, the very concept of permittivity and permeability becomes questionable. The speed limit in one-dimensional space might exist, but it would be disconnected from the electromagnetic phenomena that give the speed of light its significance in our universe. This realization illuminates a profound truth about physical constants. They are not arbitrary numbers imposed on the universe from outside, but rather they emerge from the dimensional structure of space itself. The speed of light is what it is because space has three dimensions, and because electromagnetic fields can propagate through that three-dimensional space in the specific way described by Maxwell's equations. The gravitational constant provides another example of how constants reflect dimensional structure. In our universe, gravity operates through the curvature of four-dimensional space-time, creating the rich phenomena of general relativity. In one-dimensional space plus time, gravitational effects would be severely constrained, and the gravitational constant would have a very different meaning if it could be defined at all. Planck's constant, which governs quantum mechanical phenomena, also depends on the dimensional structure of space. Quantum wave functions exist in the same three-dimensional space as classical objects, and the uncertainty principle relates position and momentum uncertainties in three-dimensional space. In one-dimensional space, quantum mechanics would be far simpler, but also far less capable of describing complex systems. The fine structure constant, which characterizes the strength of electromagnetic interactions, emerges from the interplay between electric charge, the speed of light, and Planck's constant. In one-dimensional space, where electromagnetic interactions as we know them cannot exist, this constant would lose its fundamental significance. These insights reveal that the richness of physical law in our universe is intimately connected to the richness of the space in which those laws operate. Speed limits are only meaningful when there is complex space for signals to propagate through. Interactions are only interesting when there are multiple dimensions for particles to move through. Constants are only fundamental when they govern phenomena that can actually exist. The measurement of speed itself gains meaning from dimensional richness. In our universe, we can measure velocities in any direction. We can compare speeds of objects moving in different directions, and we can analyze the components of complex motions. These measurements are meaningful because they capture real information about how objects interact with three-dimensional space. In one-dimensional space, speed measurement would be trivially simple but informationally poor. Every speed would be just a single number, positive or negative, depending on direction along the line. There would be no velocity vectors, no complex trajectory analysis, and no rich relationship between motion and the spatial framework. The very meaning of movement changes when we consider dimensional structure. In our universe, movement can be translation, rotation, vibration, or complex combinations of all three. Objects can move in straight lines, curves, spirals, or chaotic paths that explore the full three-dimensional space available to them. This variety of motion types is only possible because space has the dimensional richness to support them. Structure formation in the universe provides a cosmic example of how dimensional richness enables complexity. Galaxies, star systems, planets, and ultimately life itself all depend on the ability of matter to aggregate into complex three-dimensional structures. Gravity can create stable orbits, electromagnetic forces can bind atoms into molecules, and thermodynamics can drive the formation of organized systems. None of this would be possible in one-dimensional space. The hierarchy of structures we observe, from subatomic particles to galaxy clusters, reflects the dimensional richness of space. Each level of organization takes advantage of three-dimensional geometry to create stability, complexity, and emergent properties. Atoms are three-dimensional electron clouds around nuclei. Molecules are three-dimensional arrangements of atoms. Crystals are three-dimensional lattices of molecules. Biological organisms are three-dimensional networks of cells and organs. Information storage and processing also benefit from dimensional richness. DNA stores genetic information in the three-dimensional structure of the double helix. Proteins fold into complex three-dimensional shapes that determine their function. Brains process information through three-dimensional networks of neurons. Computer circuits are laid out in three-dimensional patterns that maximize processing power while minimizing size. Even abstract information can be visualized and manipulated more effectively in three-dimensional space. Scientists use three-dimensional models to understand molecular structures. Engineers use three-dimensional designs to create complex machines. And artists use three-dimensional forms to express ideas that cannot be captured in lower dimensions. The anthropic principle suggests that the dimensional structure of our universe might be uniquely suited to supporting complex phenomena like life and intelligence. Three spatial dimensions appear to be the minimum required for stable atomic structures, complex chemistry, and the formation of organized systems. Fewer dimensions would be too constraining, while more dimensions might make stable structures impossible. This anthropic consideration adds another layer to our understanding of why speed and light are so important in our universe. They are not just physical phenomena, they are essential components of a dimensional framework that makes complexity possible. The speed of light sets the causal structure of space-time, ensuring that information and influence propagate in an orderly fashion that allows for the formation of stable systems. As we contemplate these implications, we begin to see that our exploration of one-dimensional space has been more than just a mathematical exercise. It has been a journey of appreciation, a way of understanding why our three-dimensional universe is not just different from simpler alternatives, but profoundly richer, more beautiful, and more capable of supporting the complex phenomena we observe and experience. The speed of light, the electromagnetic spectrum, the constants of physics, and the very concept of measurement all gain their meaning from the dimensional richness of our space. By imagining what would be lost in a simpler universe, we learn to value what we have gained in our complex one. Imagine awakening in a universe fundamentally different from our own, a reality so alien that the very concept of space has been reduced to its absolute minimum. There are no stars twinkling in a vast night sky, no planets orbiting in graceful ellipses, no galaxies spiraling through cosmic distances. There is only a line, infinite and unchanging, stretching endlessly in both directions. This is the one-dimensional universe in its full, stark simplicity. And as we explore what existence might mean in such a place, we discover profound truths about why our own reality works the way it does. In this one-dimensional cosmos, the concept of space as we know it simply does not exist. There is no up or down, no left or right, no near or far in any direction, except along the single line that defines all of reality. If you could somehow exist in this universe, you would find yourself constrained to move only forward or backward along this line, with no possibility of stepping aside, looking around, or exploring in any other direction. The absence of spatial dimensionality creates a universe of unimaginable simplicity. Every location is defined by a single number, a coordinate along the line. Position 0 might mark some arbitrary reference point, position 1000 might be far to the right, and position -500 might be far to the left. But these concepts of right and left are themselves arbitrary, mere conveniences for describing motion along the only available direction. In such a universe, the very notion of stars becomes meaningless. Stars in our three-dimensional reality are massive spheres of plasma, held together by gravity operating through three-dimensional space. They shine by nuclear fusion occurring in three-dimensional cores, and they radiate energy outward in all directions through three-dimensional space. None of this is possible along a single line. There can be no spherical objects, no three-dimensional fusion processes, and no omnidirectional radiation. Similarly, planets cannot exist in one-dimensional space. Planets are three-dimensional objects with complex internal structures, atmospheric systems, and gravitational fields that extend through three-dimensional space. They orbit stars in two-dimensional ellipses embedded in three-dimensional space, with orbital mechanics that depend entirely on the geometry of higher dimensions. Reduce space to one dimension, and all of this complexity vanishes. The absence of stars and planets means the absence of everything we associate with cosmic structure. There can be no solar systems, no galaxies, no galaxy clusters. There can be no cosmic web of dark matter and ordinary matter stretching across billions of light years. The rich hierarchy of structures that characterizes our universe, from the smallest asteroids to the largest galaxy superclusters, simply cannot form when space has only one dimension. Even the concept of matter as we know it becomes problematic in one-dimensional space. Atoms in our universe are three-dimensional structures with electron clouds surrounding nuclei. The shapes of these electron clouds, the chemical bonds they form, and the three-dimensional molecules they create all depend on the three-dimensional nature of space. In one-dimensional space, it is unclear whether atoms could exist at all. And if they could, they would be utterly unlike anything we recognize. The chemistry that enables life depends entirely on three-dimensional molecular structures. DNA forms its double helix in three-dimensional space. Proteins fold into complex, three-dimensional shapes that determine their biological functions. Cell membranes enclose three-dimensional volumes, creating the boundary between inside and outside that defines cellular life. None of these structures could exist in one-dimensional space. Without chemistry, without molecular biology, without the complex interactions that enable life, the one-dimensional universe becomes a realm of abstract mathematical entities rather than physical reality as we understand it. There could be no evolution, no reproduction, no growth, no metabolism. The very concept of life, which depends on organized complexity arising from three-dimensional structures, becomes meaningless. Yet even in this austere reality, certain fundamental concepts might still apply. Time could still exist as a dimension separate from the single spatial dimension. Events could still occur in sequence along the timeline, with causes preceding effects and changes happening over time. The one-dimensional universe would exist in what physicists call 1+1 dimensional space-time, with one spatial dimension and one temporal dimension. This preservation of time creates intriguing possibilities for what might exist in such a universe. Instead of particles as we know them, there might be abstract mathematical entities that exist at specific points along the line. These entities might have properties like mass, charge, or energy, even if they cannot have the complex three-dimensional structures we associate with particles in our universe. These hypothetical one-dimensional entities might interact with each other, but only in the most limited ways. Two entities at the same location would necessarily interact directly. Two entities at different locations could only interact if some form of signal or force could propagate along the line between them. There would be no way for entities to avoid each other, no way to orbit around each other, and no way to form complex bound systems. The motion of entities in one-dimensional space would be constrained to the ultimate simplicity. Each entity could move forward or backward along the line, accelerating or decelerating under the influence of forces, but never deviating from the straight path. There would be no circular motion, no oscillation in multiple directions, no complex trajectories that explore three-dimensional space. Collisions in this universe would be inevitable and absolute. If two entities are moving toward each other along the line, they must eventually meet. There is no way to swerve, no way to pass by each other, no way to avoid collision. Every encounter would be a head-on collision, with the entities either bouncing off each other, sticking together, or passing through each other, depending on the nature of their interaction. The concept of causality would take on a peculiar character in one-dimensional space. In our universe, cause and effect can propagate in all directions, creating complex networks of causal relationships. In one-dimensional space, causality could only propagate forward and backward along the line. An event at position 0 could potentially influence events at positions 100 and -100, but the causal relationships would be strictly linear. This linear causality would create a universe with no complex causal networks, no feedback loops, and no emergent behaviors arising from the interaction of many components. Everything would be reducible to simple chains of cause and effect stretching along the line. There could be no parallel processing, no redundancy, and no resilience to disruption. The absence of geometry in one-dimensional space eliminates many of the mathematical structures that make our universe interesting. There would be no circles, no spheres, no complex curves winding through space. There would be no surfaces, no volumes, no topological features like holes or knots. The rich field of geometry, which has inspired mathematics and physics for thousands of years, would be reduced to the study of line segments and points. Symmetry, which plays such an important role in physics, would be severely limited in one-dimensional space. There could be reflection symmetry, where the universe looks the same when you flip left and right. There could be translation symmetry, where the universe looks the same when you shift position along the line. But there could be no rotational symmetry, no three-dimensional symmetry groups, and no complex symmetry operations that relate different orientations in space. The forces of nature would be fundamentally altered in one-dimensional space. Gravity, if it could exist at all, would be a simple attractive force pulling objects together along the line. There could be no orbital mechanics, no tidal forces, and no gravitational waves. Electromagnetic forces would be impossible in their usual form, since electromagnetic waves require multiple dimensions to propagate. Even if some simplified version of electromagnetism could exist in one-dimensional space, it would lack the richness that makes electromagnetic phenomena so important in our universe. There could be no electromagnetic spectrum, no light, no radio waves, no X-rays. There could be no magnetic fields as we know them, since magnetic fields require multiple dimensions to define their direction and orientation. The strong and weak nuclear forces, which operate at subatomic scales in our universe, would also be fundamentally altered. These forces depend on complex quantum field configurations in three-dimensional space. In one-dimensional space, it is unclear whether they could exist at all, and if they could, they would be far simpler than their three-dimensional counterparts. Conservation laws, which play such an important role in physics, would be simplified in one-dimensional space. Energy conservation would still apply, but momentum conservation would be reduced to a single component along the line. Angular momentum conservation would be impossible, since there would be no rotation. The rich interplay between different conservation laws that governs complex physical processes would be greatly reduced. Thermodynamics would face fundamental challenges in one-dimensional space. The statistical mechanics that underlies thermodynamics depends on the ability of particles to explore different configurations in space. In three-dimensional space, there are vast numbers of possible arrangements for any collection of particles. In one-dimensional space, the number of arrangements would be severely limited, potentially eliminating many thermodynamic phenomena. Heat flow, which depends on the random motion of particles in three-dimensional space, would be reduced to simple diffusion along the line. There could be no convection, no radiation, and no complex heat transfer mechanisms. The second law of thermodynamics, which describes the increase of entropy over time, might still apply, but entropy itself would have a much simpler meaning. Information theory would also be impacted by the dimensional constraints. In our universe, information can be stored and processed using three-dimensional structures, with vast amounts of data encoded in the spatial arrangements of atoms and molecules. In one-dimensional space, information storage would be limited to sequences of states along the line, like a one-dimensional version of digital storage. The processing of information would be severely constrained by the linear nature of one-dimensional space. There could be no parallel processing, no two-dimensional or three-dimensional computational architectures, and no complex networks for information flow. Every computation would be essentially sequential, processing information one step at a time along the line. Communication in a one-dimensional universe would be limited to sending signals forward and backward along the line. There could be no broadcasting, no networking, no complex communication protocols that take advantage of three-dimensional space. Every message would have to travel through every point between sender and receiver, creating potential bottlenecks and limiting the complexity of communication systems. The mathematical description of one-dimensional physics would be far simpler than our three-dimensional physics, but also far less rich. Differential equations would be ordinary rather than partial, since there would be only one spatial variable. Vector calculus would be reduced to simple calculus along the line. The complex mathematical structures that make modern physics so powerful and beautiful would be greatly simplified. Yet this simplicity would come at an enormous cost in terms of the phenomena that could exist. The one-dimensional universe would be a place of mathematical purity but physical poverty, where abstract principles could be studied in isolation, but where the complex, beautiful, and life-supporting phenomena of our universe could never arise. As we contemplate this stark alternative to our reality, we begin to appreciate the profound gift of three-dimensional space. The complexity that sometimes seems overwhelming in our universe, the richness that can be difficult to comprehend, and the beauty that emerges from the interaction of simple laws in complex geometries all depend on the dimensional structure that we take for granted. The one-dimensional universe serves as a mirror, reflecting back to us the extraordinary nature of our own reality. In its austere simplicity, we see more clearly the abundance of our three-dimensional world. In its limitations, we understand the freedom that dimensional richness provides. In its impossibility of supporting life and complexity, we recognize the remarkable suitability of our universe for the emergence of structure, beauty, and consciousness itself. After wandering through the austere landscape of one-dimensional space, we return to our own universe with new eyes, like travelers who appreciate home only after experiencing a foreign land. The three-dimensional space that surrounds us, which we navigate so effortlessly that we rarely think about it, reveals itself to be not just a stage for physical phenomena, but the very foundation that makes complexity, beauty, and life itself possible. Every breath we take, every step we make, every thought we think, depends on the rich dimensional structure that we have learned to see with fresh appreciation. Our three-dimensional space allows light to radiate outward from every source, creating the expanding spheres of electromagnetic energy that illuminate our world. When the sun rises each morning, it sends light racing outward in all directions simultaneously at the speed of light, creating an ever-expanding sphere of photons that eventually reaches Earth. This spherical expansion is only possible because space has 3 dimensions for the light to spread through. The electromagnetic waves that constitute this light oscillate in planes perpendicular to their direction of travel, with electric and magnetic field components that dance together in the 3-dimensional framework of space. These oscillations create the rich electromagnetic spectrum, from the long radio waves that carry our communications to the short gamma rays that reveal the most energetic processes in the cosmos. Each frequency carries its own energy, its own possibilities, its own role in the grand symphony of electromagnetic phenomena. The colors we see, the warmth we feel from sunlight, the ability of plants to convert light into chemical energy through photosynthesis, all depend on this 3-dimensional propagation of electromagnetic waves. In 1-dimensional space, none of this would be possible. There would be no rainbow after a storm, no blue sky during the day, no stars visible at night. The universe would be dark in a way that goes beyond the mere absence of light, dark with the absence of the very possibility of illumination. Gravity in our 3-dimensional universe creates the cosmic architecture we observe. Stars form from gravitational collapse in 3-dimensional space, creating spherical objects where nuclear fusion can occur in 3-dimensional cores. These stars then attract planets, which orbit in elliptical paths that explore the 3-dimensional gravitational field surrounding the star. The gravitational interaction between multiple bodies creates complex orbital dynamics, with planets and moons dancing in intricate patterns that would be impossible in lower dimensions. The curvature of space-time described by Einstein's general relativity requires 3 spatial dimensions plus time to achieve its full expression. Massive objects curve the 4-dimensional space-time continuum, and this curvature guides the motion of other objects along geodesics through the curved geometry. Gravitational waves, ripples in space-time itself, propagate outward from accelerating masses, carrying information about cosmic events across the universe at the speed of light. These gravitational phenomena enable the formation of stable structures throughout the cosmos. Galaxy clusters hold together under their own gravity, containing hundreds or thousands of individual galaxies. Within each galaxy, billions of stars orbit the galactic center in complex patterns that depend on the 3-dimensional distribution of matter and dark matter. Solar systems form when gravity creates stable orbits for planets around stars, and these systems can persist for billions of years because of the stability provided by 3-dimensional orbital mechanics. Our own solar system demonstrates the rich dynamics that emerge from 3-dimensional gravity. The 8 planets orbit the Sun in ellipses that lie in nearly the same plane, but small deviations from perfect circularity and coplanarity create complex perturbations. Jupiter's massive gravity influences the orbits of asteroids, creating gaps in the asteroid belt and shepherding some asteroids into stable orbits. The gravitational interactions between planets cause their orbits to precess slowly over millions of years, creating long-term changes in Earth's climate through the Milankovitch cycles. The Moon's orbit around Earth demonstrates another layer of 3-dimensional complexity. Tidal forces, which arise from the 3-dimensional nature of gravitational fields, cause the Moon to gradually spiral away from Earth while simultaneously slowing Earth's rotation. These tidal effects create the ocean tides that have shaped the evolution of life on our planet, providing energy and mixing that helped drive the chemical processes leading to the first living organisms. Chemistry, the foundation of all life on Earth, depends entirely on the 3-dimensional structure of atoms and molecules. Electrons occupy 3-dimensional orbitals around atomic nuclei, creating the complex shapes and energy levels that determine how atoms can bond with each other. The geometry of these bonds, the angles between them, and the 3-dimensional shapes of the resulting molecules all emerge from the quantum mechanical properties of electrons moving in 3-dimensional space. Water, the essential medium for life as we know it, demonstrates the importance of three-dimensional molecular structure. The water molecule has a bent shape with an angle of about 104 degrees between the hydrogen-oxygen bonds. This specific geometry, which results from the three-dimensional arrangement of electron orbitals, gives water its unique properties. Water molecules can form hydrogen bonds with each other, creating the liquid phase that exists at Earth's surface temperature and the ice phase that floats on liquid water. These properties of water enable countless biological processes. Water serves as a solvent for biochemical reactions, a medium for transporting nutrients and waste products, and a participant in many metabolic processes. The three-dimensional structure of water molecules allows them to surround and stabilize other molecules, to form the aqueous environment inside cells, and to participate in the complex folding of proteins into their functional three-dimensional shapes. Proteins themselves demonstrate the crucial importance of three-dimensional structure in biology. Every protein begins as a linear chain of amino acids, but this chain folds into a specific three-dimensional shape that determines the protein's function. Enzymes achieve their catalytic activity through the precise three-dimensional arrangement of atoms in their active sites. Structural proteins, like collagen, form three-dimensional networks that provide mechanical support for tissues. Transport proteins create three-dimensional channels that allow specific molecules to pass through cell membranes. DNA, the molecule that stores genetic information, forms its famous double helix structure in three-dimensional space. The two strands of the helix are held together by hydrogen bonds between complementary base pairs, and the entire structure is stabilized by the three-dimensional geometry of the sugar phosphate backbone. This three-dimensional structure enables DNA replication, where the two strands separate and serve as templates for creating new complementary strands. The genetic code itself depends on three-dimensional molecular recognition. Transfer RNA molecules have complex three-dimensional structures that allow them to recognize specific codons on messenger RNA and carry the corresponding amino acids to the ribosome. The ribosome itself is a massive three-dimensional molecular machine that translates the linear genetic code into three-dimensional proteins. Cellular biology exploits three-dimensional space at every level of organization. Cell membranes enclose three-dimensional volumes, creating the fundamental distinction between inside and outside that defines living cells. Organelles within cells are three-dimensional structures, specialized for different functions. Mitochondria have complex, three-dimensional internal membranes that maximize the surface area available for energy production. The endoplasmic reticulum forms a three-dimensional network of membranes where proteins are synthesized and modified. The nervous system represents perhaps the ultimate expression of three-dimensional biological complexity. Neurons extend three-dimensional dendrites and axons that form intricate networks throughout the brain and body. The human brain contains approximately 86 billion neurons, each connected to thousands of others through three-dimensional networks of synapses. This three-dimensional architecture enables the parallel processing, pattern recognition, and complex information integration that underlie consciousness and intelligence. Our fundamental constants emerge from and depend on this three-dimensional structure. The speed of light c is determined by the properties of electromagnetic fields in three-dimensional space. Planck's constant h governs quantum mechanical phenomena that occur in three-dimensional atomic and molecular systems. The gravitational constant g describes how matter curves three-dimensional space according to Einstein's field equations. The fine structure constant characterizes electromagnetic interactions between three-dimensional atomic structures. These constants are not arbitrary numbers imposed on the universe from outside. They emerge from the dimensional structure of space itself, from the ways that fields and particles can interact in three-dimensional geometry, and from the quantum mechanical properties of matter in three dimensions. Change the dimensional structure, and these constants would either disappear entirely or take on completely different values with completely different meanings. The measurement systems we use to quantify physical phenomena reflect this dimensional richness. Our units of length, area, and volume are based on three-dimensional geometry. Our understanding of velocity, acceleration, and force incorporates three-dimensional vector quantities. Our concepts of energy, momentum, and angular momentum all depend on three-dimensional physics. Even time, though conceptually separate from space, is measured against the background of three-dimensional processes like atomic oscillations and planetary motions. Technology in our civilization exploits three-dimensional space in countless ways. Buildings use three-dimensional structures to enclose space efficiently and resist gravitational and wind forces. Transportation systems navigate through three-dimensional space with vehicles that can move forward, backward, left, right, up, and down. Communication systems use electromagnetic waves that propagate through three-dimensional space, carrying information across vast distances at the speed of light. Electronics and computing demonstrate the power of three-dimensional design. Integrated circuits pack billions of transistors into three-dimensional arrangements that maximize processing power while minimizing size. Computer memories store information in three-dimensional arrays of cells. Network systems route information through three-dimensional topologies that provide redundancy and efficiency. Even abstract information processing benefits from three-dimensional thinking. We visualize complex data using three-dimensional graphs and models. We design algorithms that take advantage of three-dimensional data structures. We solve problems by exploring three-dimensional solution spaces that would be impossible to navigate in lower dimensions. Art and culture reflect our deep appreciation for three-dimensional beauty. Sculpture explores form and space in three dimensions. Architecture creates three-dimensional environments that shape human experience. Music, though temporal rather than spatial, often uses three-dimensional metaphors like high and low, near and far, to describe its emotional and aesthetic effects. The anthropic principle suggests that three-dimensional space may be uniquely suited for supporting complex phenomena like life and intelligence. Fewer dimensions would be too constraining to allow for the complex structures and interactions needed for biology. More dimensions might make stable atomic and molecular structures impossible, preventing the formation of the building blocks of life. This anthropic consideration helps us understand why our universe has the dimensional structure it does. We exist in three-dimensional space not because it is the only possible choice, but because it is the choice that enables our existence. The dimensional structure of our universe is fine-tuned to support the complex chemistry, stable astronomical systems, and rich information processing that make life and consciousness possible. The constants of physics, from the speed of light to Planck's constant to the masses of fundamental particles, are similarly fine-tuned to work together in three-dimensional space. These constants form a coherent system that enables atoms to exist, stars to shine, planets to form stable orbits, and complex molecules to evolve into living systems. Our journey through one-dimensional space has shown us that dimensionality is not arbitrary. The richness of our universe, the beauty of natural phenomena, and the very possibility of life all emerge from the specific dimensional structure of the space we inhabit. We live in a universe where space has exactly the right number of dimensions to support complexity, where the fundamental constants have exactly the right values to enable stable structures, and where the laws of physics work together to create a cosmos capable of understanding itself. As we prepare to explore even deeper questions about the nature of space and time, we carry with us this new appreciation for the dimensional foundation of reality. The three dimensions that surround us are not just empty space waiting to be filled, but the active, dynamic framework that makes everything else possible. In learning to see dimensions as fundamental rather than incidental, we prepare ourselves to consider whether our familiar three-dimensional space might itself be just one layer of an even richer, more complex reality. Our exploration of one-dimensional space has revealed the profound importance of dimensionality in shaping the nature of reality. But what if our journey into simplified dimensions has been looking in the wrong direction? What if, instead of fewer dimensions, our universe actually contains more dimensions than the three of space and one of time that we directly experience? This possibility, which emerges from some of the most advanced theories in modern physics, opens extraordinary new perspectives on the nature of light, speed, and the fundamental limits of reality itself. The idea that our universe might contain hidden dimensions beyond the familiar three of space is not mere science fiction speculation. It arises from serious attempts to understand some of the deepest puzzles in physics. String theory, one of the most ambitious theoretical frameworks ever developed, suggests that the fundamental building blocks of reality are not point particles, but tiny vibrating strings that exist in a space with many more than three spatial dimensions. In string theory, the universe may contain as many as 10 or 11 total dimensions, with most of them compactified or curled up so tightly that we cannot directly observe them. These extra dimensions would be present at every point in our familiar three-dimensional space, but they would be so small, perhaps close to the Planck length of about 10 to the minus 35 meters, that they remain hidden from our everyday experience and even from our most sensitive scientific instruments. The compactification of extra dimensions can be visualized by imagining a garden hose viewed from a great distance. From far away, the hose appears to be a one-dimensional line, but as you get closer, you discover that it actually has additional dimensions wrapped around the line. The hose has circumference and thickness that become apparent only when you examine it at sufficiently small scales. Similarly, each point in our three-dimensional space might have additional dimensions curled up in complex geometric structures that we cannot perceive. These hidden dimensions could fundamentally alter our understanding of how light behaves and what determines its speed. In our familiar three-dimensional space, light travels as electromagnetic waves, with electric and magnetic field components oscillating perpendicular to each other and to the direction of propagation. But if extra dimensions exist, electromagnetic fields might extend into those dimensions as well, potentially changing the way light propagates and the speed at which it travels. The mathematics of electromagnetic theory in higher dimensional spaces becomes extraordinarily complex. Maxwell's equations, which describe electromagnetic phenomena in our three-dimensional world, must be generalized to account for field components in all available dimensions. The relationship between electric permittivity, magnetic permeability, and the speed of light, which gives us CE equals 1 over the square root of permittivity times permeability in 3 dimensions, would need to be recalculated for the full higher dimensional space. Different compactification schemes for the extra dimensions could lead to different effective values for electromagnetic properties in our 3-dimensional subspace. The way the extra dimensions are curled up, their size, their topology, and their geometric properties could all influence the behavior of electromagnetic fields and potentially alter the speed of light that we observe in our 3-dimensional experiments. Some theoretical models suggest that light might actually travel through the extra dimensions, as well as through our familiar 3 dimensions. If this were the case, light might take shortcuts through higher dimensional space that could effectively allow it to travel faster than CE, as measured in our 3-dimensional framework. This possibility is reminiscent of the old science fiction concept of hyperspace, where travelers could take shortcuts through higher dimensions to reach distant destinations faster than light traveling through normal space. However, such shortcuts would not violate the fundamental principle of relativity if the speed of light in the full higher dimensional space remained constant. Instead, They would represent a different geometry for light propagation, where the shortest path between 2 points in our three-dimensional space might actually curve through the extra dimensions. The study of extra dimensions has also led to speculation about the possibility of gravitational effects leaking into or out of our three-dimensional space. In theories with large extra dimensions, gravity might spread out into the additional spatial dimensions, potentially explaining why gravity appears to be so much weaker than the other fundamental forces. This could have implications for understanding dark matter and dark energy, the mysterious components that seem to dominate the energy content of our universe. If gravitational effects can propagate through extra dimensions, then gravitational waves might also take advantage of higher dimensional shortcuts. Gravitational wave detectors like LIGO and Virgo measure ripples in space-time that travel at the speed of light through our three-dimensional space. But if gravity can propagate through extra dimensions, there might be additional gravitational wave signals that take different paths and arrive at different times. The possibility of extra dimensions also opens up new perspectives on the fundamental constants of physics. The values of constants like the speed of light, Planck's constant, and the gravitational constant might not be truly fundamental, but might instead be effective values that emerge from the compactification of extra dimensions. Different compactification schemes could give rise to different effective constants, potentially explaining why these constants have the particular values we observe. Kaluza-Klein theory, an early attempt to unify gravity and electromagnetism, proposed that our four-dimensional spacetime is actually a slice of a five-dimensional space. In this theory, electromagnetic phenomena arise from gravitational effects in the fifth dimension. The compactification of the fifth dimension determines the strength of electromagnetic interactions and potentially the speed of light in our four-dimensional spacetime. More modern versions of Kaluza-Klein theory and string theory explore even higher dimensional spaces with complex compactification schemes. These theories suggest that all the fundamental forces, including the strong and weak nuclear forces, as well as gravity and electromagnetism, might arise from geometry in higher dimensional spaces. The way these dimensions are compactified could determine not only the strengths of the forces, but also the speeds at which different types of signals propagate. Some versions of string theory include objects called branes, short for membranes, which are extended objects that can exist in the higher dimensional space. Our familiar three-dimensional space might actually be a three-dimensional brane embedded in a higher dimensional space called the bulk. Matter and electromagnetic fields might be confined to our brane, while gravity can propagate through the full higher dimensional bulk. This brane world scenario could lead to fascinating possibilities for transcending the speed of light limit in our three-dimensional space. While light and matter would be confined to travel within our brane at speeds no greater than c, information might potentially be transmitted through the bulk at different speeds. Gravitational signals or other bulk phenomena might provide ways to send information between distant points on our brane faster than light traveling along the brane surface. The concept of wormholes, which are hypothetical tunnels through space-time that could connect distant regions of the universe, becomes more plausible in higher dimensional theories. While wormholes are extremely speculative and would require exotic matter with negative energy density to remain stable, they represent another way that the geometry of higher dimensional space could potentially allow effective faster-than-light travel without violating the fundamental speed limit in local spacetime. Wormholes would not allow objects to travel faster than light through spacetime itself, but they would provide shortcuts through spacetime that could allow travelers to reach distant destinations in less time than light traveling through normal space. The entrance and exit of a wormhole would be connected through higher dimensional space, potentially allowing for nearly instantaneous travel between points that are many light years apart in our familiar three-dimensional space. The study of black holes has also revealed connections to higher dimensional physics. The holographic principle suggests that all the information contained within a volume of space can be encoded on the boundary of that volume, much like a hologram encodes three-dimensional information on a two-dimensional surface. This principle has led to the ADS-CFT correspondence, which relates gravitational theories in higher dimensional anti-de Sitter space to conformal field theories on the boundary of that space. These holographic theories suggest that our three-dimensional reality might actually be a projection from physics occurring on a two-dimensional boundary in higher dimensional space. If this is correct, then the fundamental nature of space, time, and light might be very different from what we directly observe. The speed of light in our three-dimensional space might be an emergent property arising from more fundamental processes occurring in the higher dimensional boundary theory. Quantum entanglement, one of the most mysterious phenomena in quantum mechanics, already demonstrates that correlations between particles can be established instantaneously across vast distances. While quantum entanglement cannot be used to send information faster than light, it reveals that the quantum mechanical description of reality involves non-local correlations that transcend our classical understanding of space and time. Some theories suggest that quantum entanglement might be related to connections through higher dimensional space or through wormhole-like structures in space-time. If this is correct, then the non-local nature of quantum mechanics might provide clues about the existence of extra dimensions and their role in determining the fundamental properties of our universe. The possibility that our universe contains extra dimensions also raises questions about the ultimate nature of time. In our familiar space-time, time is treated as a single dimension that combines with three spatial dimensions to form four-dimensional space-time. But in higher dimensional theories, there might be additional time-like dimensions or more complex relationships between space and time. Some speculative theories explore the possibility of multiple time dimensions, which could lead to even more exotic possibilities for the propagation of information and the nature of causality. Multiple time dimensions might allow for closed time-like curves, time travel, or other phenomena that would fundamentally challenge our understanding of cause and effect. The experimental search for extra dimensions has become an active area of research in particle physics. High-energy particle colliders, like the Large Hadron Collider, can probe extremely small distance scales, where the effects of extra dimensions might become apparent. Scientists look for signatures such as the production of gravitons that escape into extra dimensions, modifications to gravitational forces at very short distances, or the creation of microscopic black holes. Gravitational experiments conducted in laboratories and using astronomical observations also search for deviations from Newton's inverse square law that might indicate the presence of extra dimensions. So far, these searches have not found definitive evidence for extra dimensions, but they continue to push the boundaries of our understanding and set limits on the possible size and nature of hidden dimensions. The implications of extra dimensions for our understanding of light and speed limits are profound, but still largely theoretical. If extra dimensions exist, and if they affect electromagnetic propagation, they could provide new ways to understand why the speed of light has the value it does, and whether that value is truly fundamental or merely an effective constant in our three-dimensional subspace. The possibility of transcending the speed of light through higher dimensional effects remains highly speculative, but it represents one of the most exciting frontiers in theoretical physics. Whether through shortcuts via extra dimensions, wormhole connections, or other exotic geometric effects, the existence of hidden dimensions could fundamentally change our understanding of what is possible in terms of information propagation and space travel. As we contemplate these possibilities, we must remember that they emerge from our most advanced theoretical understanding, but remain largely untested by experiment. The mathematics of higher dimensional theories is elegant and compelling, but nature may have chosen a simpler path than our theories suggest. Nevertheless, the exploration of extra dimensions has already deepened our understanding of the relationships between space, time, matter, and the fundamental constants that govern physical law. The question of whether hidden dimensions exist and whether they could change the nature of light's speed limit remains one of the great open questions in physics. As our experimental techniques become more sophisticated and our theoretical understanding continues to evolve, we may eventually discover whether our familiar three-dimensional space is the whole story or merely the visible surface of a far richer and more complex higher dimensional reality. Whether or not extra dimensions exist, our exploration of these possibilities has revealed new ways to think about the nature of space, time, and the fundamental limits of reality. In contemplating dimensions beyond our direct experience, we push the boundaries of human understanding and prepare ourselves for discoveries that might revolutionize our conception of the universe and our place within it. As our journey through the dimensions draws to a close, we find ourselves back where we began, gazing up at a night sky filled with stars whose light has traveled across vast cosmic distances to reach our eyes. But now we see this familiar scene with transformed understanding. Each photon that touches our retina carries within it the story of three-dimensional space, the legacy of electromagnetic waves propagating through the rich dimensional fabric of our universe, and the promise of mysteries that may extend far beyond what we can directly perceive. The simple act of seeing starlight represents a triumph of dimensional complexity. Light from distant suns has radiated outward in expanding spheres, navigated the three-dimensional gravitational fields of galaxy clusters, scattered off interstellar dust grains floating in three-dimensional space, and finally converged through the three-dimensional optics of our eyes to create the images of stars scattered across the celestial dome. Every step of this process depends on the dimensional richness that we have learned to appreciate through contemplating its absence. Our exploration of one-dimensional space has shown us that complexity is not accidental but essential. The universe we inhabit is not merely complicated by chance, but rather it possesses exactly the kind of complexity needed to support the emergence of structure, the evolution of life, and the development of consciousness capable of contemplating its own existence. The three dimensions of space and one dimension of time provide the minimal framework necessary for this complexity to unfold, yet they offer such richness that billions of years of cosmic evolution have only begun to explore the possibilities. The speed of light, that fundamental constant we have examined from so many angles, emerges as more than just a number describing how fast photons travel. It represents the speed at which causality itself propagates through the dimensional framework of space-time. It sets the tempo for cosmic evolution, determines the relationship between matter and energy, and provides the universal speed limit that prevents the chaos that would result if information could travel instantaneously across infinite distances. In our simplified one-dimensional universe, we discovered that even the most basic version of a speed limit would still play a crucial role in maintaining the logical structure of cause and effect. This insight reveals that speed limits are not arbitrary restrictions imposed by nature, but fundamental requirements for any universe capable of supporting coherent physical law. The constancy of the speed of light in our three-dimensional world reflects the deep principle that the laws of physics must be the same everywhere and at all times. The electromagnetic spectrum that fills our universe, from the longest radio waves to the shortest gamma rays, represents a symphony of three-dimensional wave propagation that could never exist in simpler geometries. Each frequency carries its own energy, its own possibilities for interaction with matter, and its own role in the cosmic drama. The visible light that allows us to see represents just a tiny fraction of this spectrum, yet it reveals the profound beauty that emerges when electromagnetic waves interact with the three-dimensional structures of atoms and molecules. Our contemplation of extra dimensions has opened even grander vistas of possibility. If our familiar three-dimensional space is embedded in a higher dimensional reality, then the speed of light as we measure it might be just one manifestation of more fundamental principles operating in the full dimensional space. The possibility of shortcuts through extra dimensions, wormhole connections, or other exotic geometric effects suggests that the universe might contain layers of reality beyond our direct experience. Yet whether our universe contains exactly 3 spatial dimensions or many more, the principle remains the same. Dimensionality is not incidental, but fundamental. The number and nature of dimensions determine what kinds of phenomena can exist, what kinds of interactions are possible, and what kinds of complexity can emerge. Our journey from the austere simplicity of one-dimensional space through the rich complexity of our familiar 3-dimensional world to the speculative possibilities of higher dimensional theories has revealed that dimensions are the canvas upon which the artwork of physical law is painted. The constants of physics that we have encountered throughout our exploration, from the speed of light to Planck's constant to the gravitational constant, are not arbitrary numbers, but reflections of the dimensional structure within which they operate. They emerge from the geometry of space and time, from the ways that fields and particles can interact within that geometry, and from the quantum mechanical principles that govern behavior at the smallest scales. Change the dimensions, and these constants would either disappear entirely or take on completely different values with completely different meanings. This realization suggests that our universe is not just one possibility among many, but rather it represents a remarkably special configuration of space, time, and physical law. The dimensional structure that supports our existence is neither too simple nor too complex, neither too restrictive nor too permissive. It provides exactly the right framework for atoms to form, stars to shine, planets to maintain stable orbits, and complex chemistry to evolve into the intricate molecular machinery of life. The anthropic principle, which suggests that the universe must be compatible with the existence of observers like ourselves, takes on new meaning in the context of dimensional structure. We exist in a universe with 3 spatial dimensions, not because it is the only possibility, but because it is the possibility that allows for our existence. The dimensional framework of reality appears to be fine-tuned to support the emergence of complexity, beauty, and consciousness. As we rest beneath the stars, we can appreciate the profound interconnectedness of dimensional structure, physical law, and the possibility of existence itself. The starlight that illuminates our world depends on 3-dimensional stellar cores, where nuclear fusion occurs, 3-dimensional gravitational fields that hold stars together, and 3-dimensional space through which light can propagate to carry the energy of distant suns across cosmic distances to warm our planet and power the chemistry of life. The very fact that we can contemplate these questions reflects the remarkable nature of our dimensional framework. Our brains, which are 3-dimensional networks of neurons processing information through 3-dimensional electrochemical interactions, have evolved the capacity to imagine simplified universes, to explore mathematical abstractions, and to wonder about realities beyond our direct experience. This capacity for abstract thought represents one of the most extraordinary emergent properties of 3-dimensional complexity. The beauty we perceive in the night sky, in the mathematical elegance of physical law, and in the intricate structures revealed by scientific investigation, all emerge from the interplay between mind and cosmos within our 3-dimensional framework. Beauty is not just a subjective human experience, but a reflection of the deep harmonies that arise when consciousness encounters the dimensional structure of reality. Our exploration has revealed that simplification can illuminate complexity, that contemplating what is not possible can help us appreciate what is possible, and that the journey toward understanding often leads us not to final answers but to deeper questions. The mystery of why our universe has the dimensional structure it does, why the constants of physics have the values they do, and why complexity and consciousness have emerged from simple physical law remains as profound as ever. Yet in wrestling with these mysteries, we participate in one of the most remarkable phenomena in the known universe: the capacity of matter organized in three-dimensional space to understand itself. We are arrangements of atoms and molecules that have become aware of their own existence, capable of contemplating the nature of space and time, and able to appreciate the beauty and mystery of the cosmos from which we emerged. The speed of light, which has served as our guide throughout this journey, continues to race through three-dimensional space, carrying information from the most distant galaxies, revealing the history of cosmic evolution and connecting every corner of the observable universe in a web of causal relationships. In the time it has taken for these thoughts to unfold, countless photons have traveled countless kilometers, carrying the energy and information that sustain the ongoing evolution of our cosmos. As we close our eyes and drift towards sleep, we can rest in the knowledge that we inhabit a universe of extraordinary richness and beauty. The three-dimensional space that surrounds us is not empty void, but the active, dynamic framework that makes everything else possible. The speed of light that sets the tempo of cosmic evolution continues its eternal dance through the dimensional fabric of space-time, ensuring that cause follows effect, that information propagates in orderly fashion, and that the universe maintains its coherent structure across space and time. In our dreams, perhaps we will continue to explore the infinite possibilities that emerge from the interplay of dimensions, constants, and physical law. Perhaps we will journey again through one-dimensional simplicity to three-dimensional richness to higher dimensional speculation. Perhaps we will discover new ways to appreciate the remarkable nature of the reality we inhabit and our extraordinary privilege to be conscious observers within it. The stars continue their eternal vigil overhead, their light carrying messages across the cosmic void, their existence testament to the power of three-dimensional space to support complexity, beauty, and the ongoing story of cosmic evolution. In their light, we find both the humility that comes from recognizing our small place in a vast universe, and the wonder that comes from understanding our unique capacity to comprehend that universe and our place within it. Rest now beneath the infinite stars, dream of infinite dimensions, and wake tomorrow with renewed appreciation for the extraordinary three-dimensional world that makes our existence possible. The mystery continues, the exploration never ends, and the universe awaits our ongoing attempts to understand the deep principles that govern space, time, light, and the endless dance of existence itself.